Swayam Prabha. Digital India. Educated India.
Welcome to lecture 38 on time series modeling and forecasting. In the last lecture, we discussed the problem of spurious regression. That is, suppose you have two independent I1 processes and you run the regression between them, then your regression results are not very reliable. Sometimes you may observe a strong relationship between two processes, whereas two processes are independently distributed. So, this is the problem of spurious regression, and this problem arises because both the processes are I1 processes. Then if you have two processes which involve a common stochastic trend, that is a common I1 process, then you observe that you can run the regression between two processes. And probably the reason is the presence of that I1 process in both the variables. Such kind of variables can be written as a linear combination of those variables, which is I0. Means suppose x t is an I1 process, y t is an I1 process, and both the processes have a common stochastic trend. Then you can get a vector beta such that beta transpose x t y t is I0 process. Such a vector is called cointegrating vector, and such a process is called cointegrated process. Then we also discussed the error correction model. The beauty of error correction model is that suppose you have V vector autoregressive process of order p involving I1 time series or I1 variables. Then using the error correction mechanism, you can write the model or you can transform the model into a form which involves just I0 processes, provided the variables are co-integrated. Then we also discussed the definition of co-integration. In this lecture, we will consider the co-integration analysis of bivariate time series processes, and then we will extend it for the processes involving more than two time series also. So, first we consider the co-integration for bivariate processes. Suppose x t and y t are two I1 processes. Now, suppose there exists a parameter b such that y t minus b x t is equal to z t plus a, and this y t minus b x t is stationary. Then we say that x t and y t are co-integrated, and in this equation 1, z t is a stationary process, and then the corresponding equilibrium relation is, as t tends to infinity, you get the equilibrium relation. Since z t is a stationary process, this goes to 0 as t tends to infinity. So, you get the equilibrium relation y equal to A plus Bx. A is called the level of equilibrium relation, and suppose you take this 2 cross 1 vector beta. So, that beta transpose is equal to 1 minus B, then this is called the co-integration vector. In fact, if you write beta transpose y t x t, this is an I0 process. So, that is why this beta is called the co-integration vector. Z is the deviation from the equilibrium, that is equilibrium error. Further, Z has finite variance. So, the deviations from the equilibrium are bounded because Z has finite variance. So, the deviations will be bounded because, and the system is always returning to its equilibrium path. So, in this sense we say that this equation 2 is an attractor. This equation is called an attractor. Ultimately, the process is attracted towards this equilibrium equation. Then co-integration of x and y implies that both variables follow a common stochastic trend, and then we model the common stochastic trend as a random walk. Say W t is equal to W t minus 1 plus U t. Again, U t is a white noise process. Then the two co-integrated I1 processes can be represented as y t is equal to B W t plus y t curl, where y t curl is I0 process, and x t is equal to W t plus x t curl, where x t curl is also I0 process. So, this W t is common to both y t and x t, or you can say both the processes y t and x t have a common stochastic trend, which is W t. Now, if you take the linear combination y t minus b x t, then y t minus b x t is equal to y t curl minus b x t curl, and you write it equal to say z t, then this y t curl minus b x t curl or z t is actually a linear combination of two I0 processes. So, since this is a linear combination of two I0 processes, so it is also I0 or stationary. So, this 6 is the co-integrating equation. Y t has a stochastic trend, x t has a stochastic trend. Well, this linear combination y t minus b x t is I0 process. So, that is why this relation y t minus b x t is the co-integrating relation. Now, for k variable case, the error correction representation is delta y t is equal to small delta minus a I y t minus 1 plus summation j equal to 1 to p minus 1 a j star delta y t minus j plus u t. We actually derived this error correction representation in the last lecture. Then suppose we consider the bivariate case, then delta y t is equal to delta y t delta x t, say you have 2 times these y t and x t. Then small delta we write it equal to A naught B naught. A I is written as say small gamma y then minus b gamma y gamma x minus b gamma x. U t is equal to u y t u x t, and A j star is equal to A y j A x j B y j B x j. So, A j star is 2 by 2 matrix. The elements of A j star are A y j, A x j, B y j and B x j. Then in the bivariate case, you get the reduced form. Say delta y t is equal to A naught minus gamma y, you have y t minus 1 minus B x t minus 1 plus says summation j equal to 1 to p x A x j delta x t minus j plus summation j equal to 1 to p y A y j delta y t minus j plus u y t. And for x t you have delta x t equal to say b naught minus gamma x x t minus 1 minus b y t minus 1 plus summation over j equal to 1 to q x b x j delta x t minus j plus summation j equal to 1 to q y b y j delta y t minus j plus u x t. We are using all these notations, and if we use these notations for this k variable error representation, then we get this representation. This delta y t involves these p x lagged values of delta x t and p y lagged values of delta y t. Similarly, delta x t involves q x lagged values of delta x t and q y lagged values of delta y t. Then the representation contains stationary variables, although the underlying relation is between non-stationary I 1 variables. So, your original process was involving I 1 variables, but this error correction representation has all the stationary variables. Now, suppose you fit the model only for the first differences, then you are going to miss this equilibrium term y t minus 1 minus b x t minus 1 or x t minus 1 minus b y t minus 1. You remember that in the last lecture, we considered a simulated data on x t and y t. Both the processes had a common stochastic trend. Then we had taken first differences to make the processes stationary. Then we run regression between the two processes, and then we observed that for that simulated data, that performance of the regression was very poor. The regression had very low R square, and this was the reason, because we did not consider this equilibrium term. We were just running the regression between the first differences. So, this term was missing, and actually these are the terms which provide the long term relationship between x and y. So, if you are just running the regression between first differences, if you think that you have converted the I 1 processes into I 0 processes just by taking the first differences, now you can run the regression. Then your inferences may not be proper, because you are missing an important term, and that important term is this equilibrium term, and this is actually the term which represents the long term relationship between y and x. So, you are missing the long term relationship between y and x or x and y. Now, if x and y are co-integrated, at least one gamma I is different from 0. So, one of these gammas means either gamma x or gamma y is different from 0. If both are 0, then x and y are not co-integrated, and there is no long term relationship between x and y. So, suppose you want to test whether x and y have long term relationship or not, then you have to test the hypothesis gamma x equal to 0 or gamma y equal to 0. And if the variables are co-integrated, the traditional statistical procedures can be applied, since all the variables are stationary. So, you can apply the least square procedure, you can apply t test, you can apply f test. Say just for example, for testing gamma x equal to 0, you can apply t test, or suppose you want to test the hypothesis whether these coefficients b, y, j's are 0 or not, then you can apply f test, because all the variables involved in the regression are stationary. So, this is the beauty of error correction representation. Then the system reacts to the deviations from the equilibrium relations, which is lagged by one period. So, you have equilibrium relation, and then you have deviations from the equilibrium relations, and those deviations are through these terms. And then the deviations are lagged by one period. If b is greater than 0, then equation 7 is stable whenever 0 less than or equal to gamma y less than 2, or and 0 less than or equal to gamma x less than 2, and at least one of the two parameters is different from 0. Say in the first equation, you observe that you have delta y t here and minus gamma y t minus 1 here, or you can say y t is equal to 1 minus gamma y t minus 1. And what is the condition for stationarity? 1 minus gamma y should lie between minus 1 and plus 1. 1 minus gamma y less than 1 greater than minus 1, and this implies that from here you obtain gamma y is greater than 0 and gamma y is less than 2. Now, suppose gamma x is equal to 0, then the second equation of 7 becomes delta x t is equal to b naught plus summation j b x j delta x t minus j plus summation j b y j delta y t minus j plus u x t. So, the adjustment is only possible via changes in y, means this regression has just first differences of y's. You can say that the relationship between y's and x's is through the changes in y. and there is no long term relationship. Then development of x is independent of the equilibrium error. It is the stochastic trend driving the system. In this situation, x is called weakly exogenous, means x is just governed by the changes in y. X is independent of the equilibrium error. Only the stochastic trend is driving the system, means this equation. So, in this case we say that x is weakly exogenous. In the long run, x is affecting y, but y is not affecting x. Now, if gamma x is greater than 0 and gamma y is less than 0 or vice versa, then the system might be stable, but it depends upon the other parameters. So, the following two situations can occur. The two variables are not co-integrated, then in that case both gamma x and gamma y are equal to 0. Then you say that the system contains two different stochastic trends and there is no long term relationship between two. Second, the two variables are co-integrated, that is at least one gamma I equal to x y is positive. Then the system contains one co-integrating relation and one common stochastic trend. Again, the advantage of error correction representation are error correction models measure the correction from disequilibrium of the previous period. Then the error correction models are formulated in terms of the first differences, and these models eliminate stochastic trends from the variables involved. Now, this resolves the problem of spurious regressions, because if your regression involves I1 variables, then you face the problem of spurious regression. And since your error correction representation does not involve any I1 variables, so it resolves the problem of spurious regression. Then, since all the variables are stationary or I0 variables, they can be easily fitted using say a method of least squares, or you can also use any other inference procedure for the error correction model. Then the disequilibrium error term is a stationary variable. So, the co-integrated variables imply that there is some kind of adjustment process preventing the errors in the long run relationship from becoming larger and larger. Now, if the variables are not co-integrated, then this disequilibrium error may be non-stationary. Means your processes may be moving in entirely different directions in the long run. So, in that case the variables do not have any long run relationship, but if the disequilibrium error is stationary, then this prevents the two variables moving far from each other, or in the long run you can say that there is some adjustment process working which prevents the errors in the long run relationship from becoming larger and larger, or which preventing the two series to move in different directions. So, this is another advantage of error correction model or error correction representation. Now, we consider this example of ARIMA 110 process. So, since the process is integrated of order 1, so first difference is delta x t follow AR1 process. So, delta x t is equal to alpha plus delta x t minus 1 plus u t mod alpha is less than 1, or you can write it as 1 minus alpha delta x t equal to u t. U t is a white noise process. Y t is equal to b x t plus z t, and b is not equal to 0, say. And so z t follows AR1 process, z t equal to rho z t minus 1 plus v t. Again v t is a white noise process. Then x and y are co-integrated for mod rho less than 1. So, for mod rho less than 1 there is no problem. Now, suppose rho is equal to 1, then y t minus b x t is equal to z t, and since rho is equal to 1, z t is I1 process. So, this follows I1 process and there is no co-integration. For mod rho less than 1, y and x are co-integrated because y t minus b x t follows I0 process. For rho equal to 1 or for rho equal to 1, z t follows I1 process. So, y t minus b x t is also I1 process and there is no co-integration. Now, for rho equal to 1, the development of y is determined by two stochastic trends. X t is involved here. X t is I1 process, then Z t is also involved here, which follows I1 process. So, the development of y is determined by two stochastic trends. Then, for error correction representation, we write y t minus rho y t minus 1 equal to b x t minus rho b x t minus 1 plus v t, because z t minus rho z t minus 1 is equal to v t. Or you can say delta y t is equal to minus 1 minus rho y t minus 1 plus b 1 minus rho x t minus 1 plus b delta x t plus v t. So, you can write the model in this form. You simply take y t minus 1 in the left hand side, and then you move this rho y t minus 1 towards the right hand side. So, you get rho y t minus 1 here, and then you are subtracting y t minus from here. So, you get minus 1 minus rho y t minus 1, and then you have b 1 minus rho x t minus 1 you write here. So, you get plus b delta x t here, b x t is already here, then you get b x t minus 1 also. You are adding b x t minus 1, so you have to subtract b x t minus 1. So, you get b delta x t plus v t. Now, you substitute delta x t equal to alpha delta x t minus 1 plus u t from equation 11. Then you get delta x t equal to alpha delta x t minus 1 plus u x t, this is the first equation, and delta y t equal to minus 1 minus rho y t minus 1 minus b x t minus 1 plus b alpha x delta x t minus 1 plus u y t, where u x t is equal to u t and u y t is equal to v t plus b u t. So, we have got these two equations. The first equation has delta x t minus 1, the second equation also has delta x t minus 1 here. And this is the cointegration term y t minus 1 minus b x t minus 1. So, the equation 12 of x does not involve the equilibrium error y minus b x. So, you can say x is weakly exogenous, and this drives the whole system. Then if minus 1 less than rho less than 1, then if you write 1 minus rho equal to gamma y, then gamma y lies between 0 and 2. Thus, the system is stable and y is adjusting to the long run equilibrium. So, under this condition, you remember for rho equal to 1 we had problem. So, for rho equal to 1, that is there is no cointegration, the error correction term vanishes from 13 for rho equal to 1. This term vanishes. And the system contains two stochastic trends. So, the error correction model only contains stationary variables, the differences of I 1 variables and the stationary equilibrium error. Now, we consider the Engle and Granger two-step procedure for the cointegration analysis. So, in Engle and Granger two-step procedure, first we estimate the long run or equilibrium equation y t equal to delta naught plus delta 1 x t plus u t, and then we calculate the OLS residuals u hat t, which is equal to y t minus delta naught hat minus delta 1 hat x t. And these OLS residuals are a measure of disequilibrium. Then a test for co-integration is a test of whether u hat t is stationary or not. And for that purpose, you apply the usual ADF test, augmented Dickey-Fuller test, to the residuals. And the critical values for the ADF test are given by Mackinnon. And if co-integration holds, the OLS estimator of this 14 is said to be super consistent, and its implications are as n tends to infinity, there is no need to include I 0 variables in the co-integrating equation. If the residuals are not stationary, means involve unit root, then you do not have to include I 0 variables in the co-integrating equation. Then we estimate error correction model. Delta y t equal to phi naught plus summation over j phi j delta y t minus j plus summation over h theta h delta x t minus h plus alpha u hat t minus 1 plus epsilon t, and then we apply OLS. Now, this equation has just I 0 variables. So, there is no problem in applying OLS. And then you can also apply usual t test or even usual f test for testing different hypotheses. And you can also apply diagnostic test for error term. whether errors are autocorrelated or not, you can apply different diagnostic tests. Or you want to test the significance of different coefficients, you want to test the significance of alpha, then you can apply t-test. Say, suppose we consider this special case, delta y t is equal to phi naught plus phi 1 delta y t minus 1 plus theta 1 delta x t minus 1 plus alpha y t minus 1 minus delta naught head minus delta 1 head x t minus 1 plus epsilon t. Error correction model describes how y and x behave in the short run consistent with a long run co-integrating relationship. This part gives you the long run co-integrating relationship, and these parts are the short term corrections. Now, we consider the dynamic approach to error correction model and co-integration. Now, in equation 14, the residuals are often have serial correlation. Then the least squares estimates can be substantially biased in small samples. Then for reducing the bias, one may allow for some dynamics in the model. So, for that purpose, we apply least squares to estimate autoregressive distributed lag model y t equal to alpha plus beta naught x t minus beta 1 x t minus 1 plus gamma y t minus 1 plus epsilon t. So, instead of taking this equation y t equal to alpha plus beta naught x t plus epsilon t, we have included two more terms. One period lagged values of x and one period lagged value of y. Then for long term equation, so in the long run you can write x t equal to x t minus 1 and y t equal to y t minus 1. So, you get the relation y t equal to alpha upon 1 minus gamma plus beta naught minus beta 1 upon 1 minus gamma x t plus u t. You simply write this y t minus 1 equal to y t, take this term towards the left hand side. So, you get 1 minus gamma y t equal to alpha plus beta naught minus beta 1 x t plus epsilon t, and then finally, you get this equation. So, this is the long run equation. Then u hat t is the estimated residual from equation 15. Now, actually you are estimating this equation 15, you apply OLS to this equation and then you calculate the residuals. These u hat t are the measure of disequilibrium, just like the previous case. Then a test of co-integration is a test of whether u hat t is stationary or not. The error correction model can be estimated using the residuals from 15. If co-integration holds, the OLS estimators of 15 are super consistent. So, now we consider the general case. We can write the error correction model in this form, which we have derived earlier, and then if the rank of pi, so rank of pi is equal to k, then pi inverse exists. So, order of pi is k cross k. So, if rank of pi is k, means pi is a non-singular matrix and then its inverse exists. In that case, we can solve equation 1 for y t minus 1. As linear combination of stationary variables. So, since y t minus 1 becomes, you look at this equation, if pi y t minus 1 equal to, say, you write it z t minus 1. Now, this is stationary, then y t minus 1 is equal to pi inverse z t minus 1, then y t minus 1 is also stationary, because it is a linear combination of stationary variables. So, pi is cointegration matrix. So, it means pi y t minus 1 is stationary. So, we write it equal to z t minus 1. So, this implies that y t minus 1 is equal to pi inverse z t minus 1, which is a linear combination of I 0 variables. So, this leads to the result that y t minus 1 is also stationary. Now, this contradicts that y t is I 1 less than k, and if r is less than k, you can write pi in this form. Pi has this kind of decomposition, pi equal to gamma B transpose, where gamma is k by r and B transpose is r cross k. So, then B transpose y t are R stationary linear combinations, which guarantee that the equations of system 1 are balanced. Because you have gamma B transpose y t minus 1, or you can also write y t here. So, this is stationary, and here you have our linear combinations. So, all these linear combinations are stationary. The transpose y t has all linear combinations, all these linear combinations are stationary. So, B contains all linearly independent cointegrating vectors, gamma contains loading coefficients which measure the contributions of the R long run relations in different equations. So, it is just like the principal component analysis is in multivariate. Then system contains k minus r common stochastic trends. So, suppose rank of pi is r, then you can find this kind of matrix B, which gives you the R linearly independent cointegration vectors. Then you have R long run relations in different equations. Then the system contains k minus r common stochastic trends, and if r is equal to 0, then there is no cointegration. For testing cointegration for more than one relationships, one can use Johnson approach, which is based on ML estimation of one along with the restrictions given in equation 2. Of course, I am not going into the details of Johnson's approach here, but here I have considered an example. Now, we consider this example, we consider 3-dimensional VAR2 process. So, y t is equal to, you have this matrix which has elements 1.2, 0.7, 0.1, 0.6, 0, 0, 0.11, y t minus 1 plus then you have this matrix into y t minus 2 plus u t. So, we have VAR2 process, and then this is your A1, this is your A2. So, your A naught star is equal to minus A1 plus A2, and you can easily verify that A naught star is equal to this matrix. Just simply add A1 and A2, and then you have minus sign here. So, 1.2 minus 0.5 is 0.7, and then you have minus sign. So, you get minus 0.7 here. So, similarly, you get the other elements. Then A1 star is equal to minus A2. So, this is simply you have 0.5, then 0, then minus 0.1 is reduced to 0.1 and so on. Then we calculate the value of pi, which turns out to be 0.3, 0 minus 0.6, 0, 0, 0, 0 minus 0.5, 0.2. So, the rank of pi is equal to 2, you can easily verify it. So, the system has two co-integrating equations, and since you have 3 cross 1 vector here, you have 3 time series, you have 2 co-integrating vectors. So, you have one common stochastic trend. And this is the error correction representation of the process. Further, you can write pi equal to, say, in this form you can decompose pi. Say you have gamma matrix here, and then you have B here. Gamma is 0.3, 0, 0, 0, 0 minus 0.5, and this is B 1, 0 minus 0.2, 0, 1 minus 0.4. So, to obtain the long term relationship, you write B y1t, y2t, y3t. So, in fact, you get just 2 long term relationships, because B has just 2 rows. So, the 2 equations are y1t minus 0.2 y3t is equal to u1t, and y2t, because the coefficient of y1t is 0. So, you get y2t minus 0.4 y3t equal to u2t, and the common stochastic trend is delta y3t minus 1. Say in first equation you have a stochastic trend delta y1t minus 1 and delta y3t minus 1. Here you have delta y1t minus 1, delta y2t minus 1. Here you have delta y2t minus 1, delta y3t minus 1. So, for these 2 equations, the common stochastic trend is delta y3t minus 1. And then you have the equations y1t minus 0.2 y3t equal to u1t and y2t minus 0.4 y3t equal to u2t. These are the equilibrium equations, or you can write these two in this form. Y 1 t is equal to this 0.5 y 2 t plus V 1 t and y 2 t is equal to 0.4 y 3 t plus u 2 t. So, in this lecture we discussed the cointegration analysis for bivariate processes. We also discussed the Engle Granger procedure or the Engle Granger two-step procedure actually for the cointegration analysis. This procedure can be used for estimating the long run relationship. Then we also consider the case when you have more than 2 time series. We observe that if you have more than 2 time series, suppose you have k time series, then the rank of pi matrix must be less than k for the process to be cointegrated. Otherwise, all the variables will be I 0 and you will not have I 1 process. And if the rank of pi is say r, then each of the equation has k minus r common stochastic trends. So, this cointegration analysis is an important topic for establishing the relationships between non-stationary time series, particularly between different I 1 processes. And then error correction model or error correction representation plays very important role in cointegration analysis. So, I am going to stop here. Thank you.
Hello everybody, welcome back, and here I am to give a preview, very short obviously, in the area of what we mean by operation research and optimizations. So, we know operation research and optimization is used generally where you have some resources and you want to utilize them in the best possible way considering what your main objective is. Now, if we stop here and go back in the past, so the obvious question comes, from where did this technique of operation research and optimization, which is an area of mathematical techniques, come into the existence. So, generally even though the work has started from areas of mathematics, economics, but generally it is considered that operation research and optimizations were very heavily used and it became popular during World War II in trying to schedule different resources, manpower, armaments, considering there were resource constraints, time constraints and space constraints and so on and so forth. Now, for the general public, it should be aware that we consider from the academic point of view, there are different people, very famous people who have worked, but George Danzig is considered the father who really proposed the technique of linear programming as a very nice tool where you can use operation research techniques in order to optimize the resources which are there depending on different constraints which you have. And after that, things have really moved very fast, they have been developing throughout the world, they have been usage, they are different type of societies, so on and so forth. And in course of time we see and we still find exciting areas of application, but theoretically there has been a growth in techniques like robust optimization, stochastic optimization, dynamic programming, parametric programming, nonlinear programming, so on and so forth, and they are used depending on the concept and the areas of application which we see for either finance, for marketing, for scheduling, for engineering field and so on and so forth. Now, application of OR and optimization, if somebody asks, is a very difficult question to answer, because if I start now, it will almost take about 1 hour to give you all the areas of application of optimization and operation research are. But to keep it very brief, considering that you are all ready and eager to take that as a subject, I will just highlight the areas of applications, some of which are in scheduling, in assignment problem, in facility location, like you want to build up a factory, you want to build up some storehouse, so on and so forth. It is used in network flows, like you want to transport some goods, transport manpower from one area to another area. So, how we will try to basically do it in the best possible way. What is best would obviously depend on how you are trying to use optimization as a tool in different areas. It can be used, operation research and optimization can be used in health services, in financial portfolio management, asset liability management, game theory, and so on and so forth. Now, in the recent past, even though it is very well known, but still I would like to highlight the point that the computing powers and the techniques of operation research and obviously in statistics has exponentially grown. And with very sophisticated programming being available, like we know that there is MATLAB, there is R, there is SAS, which are different type of optimization tools. We see nowadays that operation research and optimization is also used in health sciences, in gene replication theory, in area of say for example prediction of weather, in the area of say for example prediction of earthquake, how you find out the best possible way to take actions such that it meets your overall demand. Say for example, in prediction of earthquakes, you would like to basically build up your houses, build up the dams, build up the overall locations of people staying in different localities in such a way that the minimization of the losses are sustained. Furthermore, after the advent of computing and advent of different techniques, we see many meta heuristic and heuristic techniques are very heavily used in parlance of operation research and optimization by joining them together such that you get the best benefit. So, if the question arises what are the meta heuristic techniques, I would again be very brief, because again there is a huge amount of literature, huge amount of application areas, huge amount of research which are being done in the area of genetic algorithm, taboo search, ant colony optimization, simulated annealing, then in the area of particle swarm optimization, in the area of artificial immune system, and so on and so forth. In the coming years, it is thought, and definitely with some positive viewpoint, that the area of multi-criteria decision making and multi-objective programming, where you use different type of tools and use the different advancement of optimization which has been made in such a way that you can basically optimize two different objective functions which are there in front of you, such that either if considering the area of finance, you can either maximize your return for the portfolio or minimize the risk also, or say for example, you want to basically have a layout such that minimization of cost is one factor and the maximization of say for example benefit which accrues to different type of users in this overall layout can be attained at the same time. So, obviously it means that what we are seeing is a huge application of optimization along with different type of computing and heuristic techniques, such that in years to come this area of optimization would become one of the best tools where you accrue and get the benefits in the best possible way. And I am sure that the students or the participants who will take this course will find it an exciting add-on to their CVs and to their curriculum vitae, such that they can understand the techniques, how they can be used in the best possible practical sense. Thank you.